morning, guys. I think, yeah, I still have time to say good morning. Sorry for the late. I think it is really useful information shared by the presenters. First of all, I would like to take this opportunity to thank the organizer, because it's not only a good platform to share the information, but also to gain the knowledge. Personally, I feel today I get some useful knowledge from this webinar. Thank you for that. From SIGMASOFT, I would like to present how we can optimize your rubber molding process to increase the quality and productivity. Okay. Okay, let's move on with my slides. Okay, so what we are going to discuss in this presentation. Okay, at first, I'm going to give some brief introduction to SIGMASOFT, followed by we have a compression molding simulation. In this, we will discuss about the heating up phase, multi-cycle analysis, fill behavior, preform shape, location, and size. Okay. In the second portion of this presentation, we have a case study with a curing behavior. Means we are going to optimize the curing behavior of the rubber, and we will see what is full factorial DOE and what is Sobol method, and how we optimize the process parameter for this rubber product. And after that, if we have time, then we will take some question to answer. Okay. Okay, let's move on with the Sigma. The world of Sigma. So we actually, Sigma Engineering, GmbH, is our headquarters in Aachen, Germany. It was founded in 1998. So actually, Sigma is the sister company of Magma, who is the world market and technology leader for metal casting simulation. Apart from Germany, our headquarters, we have branches all over the world. So in Singapore is actually act as the regional headquarters for Asia Pacific region. And we have branches in China, India, Korea, etc. Same. We also work with our partners all over the world. For Thailand, Sigma Solution is our partner, who is really doing a very good job there. Thank you for that. Okay, let's move on to the topic, compression molding simulation. Actually, Sigma is a dedicated software for injection molding process. But that does not mean we can not able to do other process. In SIGMASOFT, we can able to other process like as compression molding, transfer molding. It is also possible to simulate there. So why we need to do a compression molding simulation? So I list out some of the benefits here, like for mold and the machine point of view, we can understand the heating up times, how long we need to heat up, where the heat, hot spot and cold spot, and where is the, what is the heat balance, what is the energy is required to heat up the mold, what is the machine size, or what is the mold capability. With this all able to understand from this simulation. That is the mold and machine point of view. The process point of view, we can optimize to reduce the unproductive times. Like we can increase the cycle time, we can able to reduce the material wastages, and we can find out what are the significant factors that influence the process, and understanding the filling behavior, all the things. So there are many benefits using the simulation for compression molding process. Okay, we will see some of the things here. Okay, so as I mentioned, what is heating up phase? Heating up phase is actually before we start any production, we just set up the mold in the machine and we start to heat up. But how long we need to heat up? That's a question mark. Normally we heat up for 1 hour or 30 minutes, something like that. But from the simulation, it will show the exact time requirement for the heating up phases. So for these cases, this mold is heated for 1 hour, but it is not necessary. We can be able to achieve the temperature within 30 minutes. So the 30 minutes of time, it is wasted. We are not only wasting the time, we also wasting the energy. So that's what we can able to understand from this heating up phase. Then multi-cycle analysis. Multi-cycle, after heating up phases, we want to understand there will be always some differences in the temperature because the material temperature is different, and we also lose the temperature to the environment. So we want to find out at which cycle the mold is getting very less fluctuation in temperature. So that is the reason we use the multi-cycle analysis to find out the thermal steady state of the mold. For this case, you can see we use few cycles to understand, but from cycle to cycle, the difference is only 5 degrees Celsius for this case. So it is quite stable after a few cycles. Okay. Then there are filling behavior analysis. So in this filling behavior analysis, actually it provides a lot of information. This information really is useful because whenever we want to optimize the process, it is necessary to understand the process well. So to understand the process, we have this filling behavior calculation analysis. So in this you can able to get the temperature differences of the material and the changes in the velocity, the pressure requirement, what is the shear rate differences between the cavities, the scorch levels, well line, air entrapment. There are few, many results, but I listed a few here to just to highlight, and we can able to find out the loss fill areas and where are the unfilled areas, all the things we can able to find in this filling behavior analysis. Okay. Preform shape. The shape actually plays a very important role in the compression molding process, because when we have a smooth and balanced filling, which directly improves the quality of the pot. And also it's avoid the air entrapment. It does not take much wastage. Then the machine requirement also, we can use the small size machine for some cases. So I have here two different shapes here of the preform. One is the circular shape, the other one is the rectangular shape or square shape here. Then we can see how differences this preform is giving to us in terms of process. But in a result, you can see the material flow is almost same, even for these two shape preform. There is no changes in terms of temperature, and the last fill area is still same because it is located at the center with the same volume of material. So the changes is not much here. But when we have a different location and size, it is also important to be need to consider for the shape. Apart from the shape, the size and the location also important. Most of the time, we prefer the individual preform for the multi-cavity because that will give the identical distribution of material. The temperature, pressure will be the similar to all the cavities. The overflow will be reduced, all the things. But the preform, to make the preform, it takes time. So that is one of the disadvantage of having more preform. Let's see what happens if we have a different location, the size. So now you can see there are changes in the temperature. Not only temperature between in the preform, but also cavity to cavity, the temperature is differences, the last fill area is differences. So this is the reason we want to use the simulation to understand if we have the preform, what happens? It will create some well lines. So is the well line is happening on the pots or it is on the overflow area? So these are the information we can able to obtain from the simulation. Once we get all the results in SIGMASOFT, we can directly import this or export to the other FE softwares to analyze the structural analysis. So we have a features in SIGMASOFT called SigmaLink, which helps directly to transfer to export to the other FEA analysis software to continue the analysis after. So that's a summary for the first topic, first portion. So we need compression molding simulation to understand and optimize the process better. So in SIGMASOFT, it is easy to set up the simulation with the full mold and all the process parameters. It will give what is the requirement of heating up time and where the thermal steady state we achieve, all the information. It is not necessary to trial and error and waste the materials there. So we can optimize there with the SIGMASOFT simulation. For filling behavior, point of view, it will give you a lot of information like the temperature, velocity, pressure distribution, and we can find out where the well line happens, where the air entrapment happen, all the information. What is the last fill area and unfilled area, all the things we can able to find out from this compression molding simulation. Okay, let's move on to the next topic, which is a case study for curing behavior. Actually, this is a flexible coupling used in the marine industry. What happened? The material actually is a natural rubber. It is quite big size. I mean, it's around 560 mm of diameter and 15 kg of rubber itself. The weight of the rubber itself 15 kg. And we are also using a 20 kg weight of the steel material as an insert. The problem here is it takes longer cycle time to produce a single part. So we need to optimize the cycle time here, which we will see in the further slides. Let's see what happened in the current settings. The current parameters is the rubber temperature is 80 degrees Celsius, the insert temperature is 20 degrees Celsius, and the mold temperature is 140 degrees Celsius. Okay, then the heating up time, they use 5,400 seconds, which is 1 hour 30 minutes to produce one part. Let's see why they use these parameters. You can see the temperature behavior versus the curing degree. So for 1 hour 30 minutes, it takes around around 99% of the curing happen after 1 hour 30 minutes based on the current settings. But why they use this temperature? Because they also worry about the degradation. If they use the higher temperature, there is a chances of degrading the material. That's why they use 140 degrees Celsius with a longer time. So this is the current results. So we are achieving 99.5% of the curing behavior with 1 hour 30 minutes, and the degradation is 0.08%. So this is where SIGMASOFT comes here to optimize the process. The goal here is we need to increase the curing behavior with a shorter time. Is it? You can from this curve you can see when you increase the temperature, there is a high chances of reducing the curing time. So it is very simple to understand from this graph. But the problem is when we increase the temperature, it also increases the degradation behavior. So the degradation rubber lose its properties, so which is definitely not we want. So what happened in SIGMASOFT, not only the curing data set we created inside, we also include the degradation, all the degradation. We measure the degradation property and put inside the simulation to understand the degradation behavior. So now we are going to do some DOE to understand, to optimize the process. As I mentioned, the objective here is we want to reduce the curing time. That's our objective to goal to achieve. Then what are the variables we have? We have a polymer, temperature of the rubber, temperature of the insert, temperature of the mold, the upper mold and lower mold. And we also use the heating time as one of the variables. So totally we have 5 variables here. Let's in SIGMASOFT, we can set our objective. As I mentioned, we want to increase the curing behavior, and we also want to know what is the degradation behavior when we increase the curing. Then for that, we set the variables, the 5 variables with the different steps. For the mold, 100 to 220, the material is 20 to 180. So we have different steps. And after setting all the things, we achieve around 1,800 designs. We have now 1,800 designs to test. But even for simulation, to run 1,800 design, it's going to take a lot of time. But that's what we have an option called Sobol. So how the Sobol is different from full factorial DOE? Full factorial DOE is nothing but we use all the designs, which means here we need to use all the 1,800 designs to test. But Sobol method is just help us to reduce the number of designs without affecting the quality of the simulation results. For Sobol, we just need to set number of generation and designs per generation. to explain in a simple way, I just use 3 and 5 as a generation and the design per generation. So what happened in SIGMASOFT, first it's take the design per generation. Take 5 designs in the first generation randomly and do the calculation. SIGMASOFT internally analyze and evaluate the results and find out which variables is helping us to reach the goal higher. Then it focus more on the particular or the variables and focus on the select the second round of 5 designs. That's for second generation. It's do the same thing for the third generation. It select the 5 designs with the consideration of the particular variables. Then again, it's do the the third generation simulation. That's how it's come out with the best designs. So here we are going to do the same. We are not going to run the 1800 designs. We are going to take 48 designs per one generation, and we are going to use 6 generations. So total 288 designs, we are going to use it for our DOE here with the Sobol method. So for this case, it's not necessary to wait for many days. I think on the same day, you will get the results because we already reduced to 288 designs. I think it takes around 5 to 6 hours to complete all the 288 designs here. Then after the results analyze the calculation complete, you will get the overview. It is very easy to understand or identify which design is the one is giving the most curing behavior with the less degradation behavior. So you can see the rank 1 design 36 is the one giving 99.7% of the curing and also less than 0.009 percentage as the degradation. So that's the overview. But if you want to select your personalized best design, then you can use the parallel coordinate systems. Here we have variables. You can see the variables on the top in your left side. On the right side on the top, we have objectives, the degradation behavior and curing behavior. There are colorful red lines inside the plot which represent the designs, which means here we have 288 lines that represent the number of designs here. Then we have red arrows top and bottom of the plot, which help us to set the value, what we want to set to analyze. For example, let's say if I want to set the degradation to certain level, then I just pull down. Same thing for the curing behavior. I want to achieve 99 point something. So just I increase that. I just pull up. To understand the fastest cycle time, then you can just pull down the cycle time, means the mold opening time. This will give us the designs which are giving less faster cycle time. But you can see there is a extreme behavior, like we need to increase the initial temperature of the rubber to 110 degrees Celsius, and also the mold temperature we need to increase 190 degrees Celsius. This is maybe for some people it may be too extreme, but let's go back to optimize even further. Let's say we want to the temperature, the mold temperature should not be higher than 170 degrees Celsius. Then we can pull down the red arrows to set that temperature. And same thing for the insert temperature. We no need to heat up the insert. Now we can able to get optimized temperature, optimized parameters, and also we are achieving at the same level of curing behavior and degradation behavior. That's how we can achieve optimize the process. And also you can from this main effect part, you can able to see how your parameter, how your variables are influencing the your goals, your objectives. For this case, for the curing behavior, we have 5 factors, 5 variables, and each one is actually you can see each one is how it's influencing. For this case, initial temperature, yes, it plays a little part. But whereas the insert temperature, it's not really influencing the factor. But this time, the mole opening time, how long the mole inside the how long the material inside the mole is really important, because really linear expression here. Same thing for the fixed mole temperature, it's really important. Then same for the movable mole side. This is for the curing behavior. What happens to the degradation behavior? It's also kind of behave the same, but when we have a higher temperature and higher mole temperature, it really affects a lot. Let's compare the both curing and degradation. Then you can see this is increasing, whereas the insert temperature not really playing the part here. Time is really important, because you can see here at the after 1 hour, the curing behavior also increase. At the same time, the degradation also increase. So this is very sensitive here. We need to be careful here when we play with the time. Same thing for the temperature. At 130 degrees Celsius, after 130 degrees Celsius, the curing behavior is faster. And after 190 degrees Celsius, the degradation is faster. So the process window should be 130 to 190. That's important information we can get from here. Same thing for the mobile mole temperature. But this is the correlation metric which give all view in one side. So when you see red color means which means this is higher. You're supposed to put more focus on these two factors, which means here for mole temperature, fixed mole temperature, and the time, initial fixed mole temperature and the time is really important factors for our process here. So let's go back and see, compare with the current process parameters. So optimized one, if you want to achieve this better or moderate process parameter, then you can use these parameters. There is a changes in the polymer rubber temperature, also in the mole temperature. But if you want to focus on the cycle time, then you can use the second optimized parameter 2, which will, the rubber material need to be increased 100 degrees Celsius, and also the movable mole need to be increased 190 degrees Celsius. By then, you can save maximum of 75% of cycle time. This is how we can optimize our curing behavior. So the summary here is, high temperature really influence the curing and degradation of the rubber. Improves the curing with, the temperature really improves the curing with less time, but it also increases the degradation. Okay, we have really need to be take a consideration here when we increase the temperature alone. That's how in SIGMASOFT, when we use the Sobol method, even though we have made a lot of designs, we can able to reduce the number of designs and complete all the calculation with a shorter time without affecting the quality of the results. So here the heating time is reduced much lower from the initial process with the same curing and the degradation behavior. I think that's end of my slides here. We can have some question here if we have time. Otherwise, I will wait for your questions in an email form. I will try to answer through email form. Thank you very much.